In this video, we're going to look at this definite integral that has a trigonometric function in it and what we're going to do in order to integrate once we've looked at this. So the following integral we have in front of us is the integral bounded from 0 to pi thirds. And our integrand is cosine x plus sine x, and that quantity is squared, and then dx. Okay, so right now we need to look at how we're going to deal with taking the integral of this. How it's written, we don't know how to do that. I noticed that U substitution is probably not going to help me. And I noticed if I distributed this out, cosine x plus secant x times cosine x plus secant x, we would get the following. So doing that, we would get cosine squared x plus cosine x times secant x plus cosine x plus secant x, or times secant x is 2 cosine x secant x plus secant x times secant x gives us secant squared x. And then we have this dx. I know what the antiderivative of secant squared x is, because I know that if I take the derivative of tangent x, I get back secant squared x. I also know that I could rewrite secant x as 1 over cosine x. So I can rewrite this a little bit, and we can think of this as cosine squared x. Cosine squared x is where we need to do some manipulation. So we have cosine squared x plus 2 cosine x times 1 over cosine x, which is our secant x, plus secant squared x dx. So we want to go back and use one of our identities for our trigonometric function, cosine squared x. We actually want to use our half angle identity. So recall, if we had cosine of a divided by 2, and that was our angle, this would be equal to the square root of 1 plus cosine of a all over 2. So let's manipulate our cosine squared x. So recall cosine squared x, we could rewrite as cosine x. We want to manipulate this to look like a half angle identity. So let's multiply that by 2 over 2. So we would have 2x over 2. And that square is technically out here. So if I look at this and use my half angle identity, we get the square root of 1 plus cosine of 2x all over 2. We have this square here, and so we're going to square this whole thing. And so this will give us back 1 plus cosine 2x all over 2. To manipulate this to help us to be able to take the antiderivative, let's rewrite this as 2 separate fractions. So let's rewrite this as 1/2 plus cosine 2x all over 2. So rewriting our definite integral, we have the integral from 0 to pi thirds. Cosine of 2x, we just saw that's the same thing as 1/2 plus 1/2 times cosine of 2x. Bringing down our other pieces, we have plus 2 plus secant squared x. That quantity dx. I notice I can simplify this a little bit more in my integrand. I have 2 constants. I have 2 and 1/2, so I can sum those. So if I got a common denominator, that would be 4/2 plus 1/2. So this is 5/2. So I have the integral from 0 to pi thirds of 5/2 plus 1/2 cosine 2x plus secant squared x. So each term is in the form that I know how to find the antiderivative of. So let's go through and find the antiderivative of each piece, and then we're going to evaluate that from 0 to pi thirds. So the antiderivative of 5/2, so we're thinking backwards, what can I take the derivative of to get 5/2? Well, that would be 5/2 x plus 1/2. So now we're thinking, let's ignore the 2x and that cosine of 2x for a second. What do we take the antiderivative of to get cosine of x? Well, the derivative of sine is cosine, so that would be sine of the inside 2x. But when I take the derivative of this, I need to compensate for that and divide by 2 because of that chain rule. Plus, what do we take the derivative of and get back secant squared x? Well, that's tangent x. And then this whole thing is evaluated from 0 to pi thirds. Okay, so now all we need to go do is use the rule for definite integral. We're going to evaluate that antiderivative at our upper bound, pi thirds, minus our lower bound of 0. So we're looking at the antiderivative of pi thirds minus the antiderivative evaluated at 0. So plugging in this in, I get 5/2 times x, which is pi thirds, plus 1/2 times 1/2, which is going to give us the 1/4 here. Sine of 2 times pi thirds, so that's going to give me 2 pi thirds. Plus tangent of pi thirds minus, we need parentheses around this whole thing because we have more than one term. So we have 5/2 times 0 plus 1/4 sine of 2 times 0, so 0, plus tangent of 0. Simplifying this a little bit, we have 5 pi 6 plus 1/4 sine of 2 pi thirds. I know my reference angle is pi thirds. In the second quadrant, pi thirds is 60 degrees. Sine of 60 degrees is √3/2. And sine is positive in that second quadrant. So I get back √3/2 plus tangent of pi thirds, tangent of 60 degrees or tangent of pi thirds is √3 minus, well, 5/2 times 0 is 0, plus 1/4 sine of 0 is 0. So that gives me back 0, and tangent of 0 is 0. So minus 0. So my exact answer would be 5 pi 6 plus √3/8 plus √3. So in this example, you can notice that to deal with taking the antiderivative of cosine squared x, and at least in calculus 1, what we need to do is use the half angle identity. You would do the same thing as if we were taking the antiderivative of sine squared x. You're going to want to use that half angle identity and manipulate it so we could take the integral of that. Hopefully this is helpful for you.